Now we want to actually go through some simple math. Derivative. Okay, so what is the definition of derivative? Okay, if you have single variables, assuming today you have a function is a function of x, what you really do is actually d f of x dx, and then this guy we call it as derivative. And then if you want to plot these things out, okay, of course the x-axis, is x, right? Y-axis is actually your f. Let's say you have something like this. So this is going to give you the f of x. So when you do the derivative, you want to actually calculate the f between 2 points. Okay, one is at x equals to x, the other one is x plus h. If you do that calculations and then push that to the limits. Okay, so that's actually the definition of derivative of f of x. If this is actually x, this is actually x plus h. What this do on the top part is just this actually f of x plus h minus f of x. And then this is just your h, right? So the ratio between this overlap, if your h is infinitely small, then that is actually your derivative. This divided by that, that pretty much is just the slope of your curve. Let's say your function of x right now is actually a function of x, y, and z. Then your df will equals to partial f, partial x on the constant y, z times your dx plus partial f, partial y on some constant x and z times your dy plus partial f, partial z on the constant x and y dz. Okay, so this is also called the partial derivative. Okay, nothing special. For example, pressure. Let's say pressure is actually a function of V, T, let's say also N. Then I can write my dP as a function of partial P, partial V on the constant D, T, and N. This will be dV plus partial P, partial T on the constant V and N, dt plus partial P, partial N on the constant V and T. Okay, and then this terms are called the partial derivative. Let's say today I have one more ideal gas. I want to know at constant temperature how the pressure changes with your volume. How are you going to solve this? How do you translate this? So let's say things you want to figure out. Okay, so how do you do it? So ideal gas tell you what? P is equals to T over V, right? Apparently your P is a function of V and T. So you can write a partial derivative because it's constant N, right? So this one should be dN, sorry. So this term actually disappear. At constant T, right? So the second term also disappear. All you do is actually doing that. Okay, partial P, partial V, and that's the answer. So once we introduce this, there are actually 3 general rules that you want to actually memorize. Rule number 1, partial A, partial B at constant C is going to equals to 1 over partial B over partial A at constant C. Rule number 2 is partial A over partial B at constant C is going to equals to negative partial C over partial B at constant A over partial C over partial A at constant B. And this is going to equals to negative partial A over partial C at constant B, and then partial B and partial C at constant A. Okay, and the very last equation is partial A over partial B at constant C is going to equals to partial A over partial B at constant X plus partial A over partial X at constant B times partial X partial B at constant C. All right, so right now what I'm going to do is actually I'm going to show you how we can get these three equations. Let's say we have a pressure, okay, pressure we know is a function of V and T. Therefore, we know dP can be written as partial P partial V at constant T dV plus partial P partial T at constant V dt. Okay, I can also write V is a function of PT, right? Therefore, I can actually get dV is going to equals to partial V partial P at constant T dP plus partial V partial T at constant P dt. Let's say this is actually equation number 1. This is actually equation number 2. I'm going to rewrite this equation a little bit. Okay, so that I can write dP minus partial P over partial T at constant V dt is going to equals to partial P over partial V under constant T dV. So I'm going to divide this term both sides, okay, and I'm going to flip it. It will be 1 over partial P partial V under constant T dP minus partial P partial T at constant V divided by partial P partial V at constant T. So from here, we can write this. Okay, where I move this guy to the left. Then I divide both sides by this and then flip it, then I can get this equation. So I start from equation number 1, and then I move this term to the left, which is this term. Therefore, it becomes negative. And then on the right, what's remain is this guy, which goes to that guy. And then I divide this guy on both sides. Okay, then I flip the equations. Therefore, I have this. dV equals to 1 over this term, dP minus this term. Oh, there should be actually dt here. Once I do this, then I want to compare these two equations. Okay, so both of them actually dV, right? And then they actually is written as a dP and dt, right? That means the coefficient in front of your dP should be the same. The coefficient in front of your dt should be the same, right? Therefore, I can get that this term and this term should be the same. This term and this whole term should be the same. Okay. Therefore, we learn partial V, partial P, a constant t should equals to 1 over partial p partial v a constant t. Okay, so that's the first one. The second one will be partial v partial t a constant p should equals to negative partial p partial t a constant v over partial p partial v a constant t. I'm going to let v equals to a, p equals to b, t equals to c, and then plug into here. Then I can rewrite this as partial a over partial b at constant c is going to equals to 1 over partial b over partial a at constant c. And this is our equation number 1. So using similar concept, okay, you can make b equals to a, p equals to b, p equals to c. Once you do that, you can get the equation number 2. So from the first equation, we know that, okay, let me rewrite the first equation. So we know that dp can be written as partial p partial v at constant t times dv plus partial p partial t at constant v dt. So the things I'm going to do now is actually I'm going to divide dv on both sides. So in the end, you're going to have a dp over dv is equals to partial p partial v at constant t. dv cancels out, so you don't have dv term anymore. And the second term will be partial p partial t at constant v times partial p partial v. Okay, and that's all. Once you write down this, you notice one thing. When I write partial p partial v, I did not write anything here, right? And then I did not write anything here. But every time when you write out the partial derivative, something must keep constant. Right? But when you write this, simply do these mathematical operations. You don't see anything right here. No here. But we know something must be kept constant so that you can actually do the derivative. In other words, I'm going to put something here and something here. If right now we say that A is P, B is your V, E is your C, and T is your X. So what you're going to have is actually on the left hand side will be partial A, partial B, and constant C. It's going to equals to partial A, partial B, and constant X plus partial A, partial X, and constant B, partial X, partial B, and constant C. Okay, that's how we actually get the third equation.